Okay, welcome everyone on the second day of the EVN Mini-Symposium. Now we are starting the Galactic session. I'm Anna Bartkiewicz from Toru Institute of Astronomy. This session will be co-chaired with Andreas Bruntaler from Max Planck Institute for Radio Astronomy. And please use the question and answers box, chats, and also remember that we have a discussion on the Discord. So as a first speaker, Ross Burns will be talking about VLBI monitoring of the 6.7 gigahertz methanol masers during a high mass protostellar accretion burst. Ross, please. Please share the screen. Yes, we are seeing it. And yes, we see the cursor. Yes. Okay, let's start.
Okay. So thanks to the organizers for setting up this conference. I think even 2 years between EVN symposia is too much, but 4 years is definitely way too much. So yeah, having something in between was definitely a good choice. And I'm really grateful for having the opportunity to talk to everyone again and see everyone on Discord and all this stuff. So yeah, just thank you very much. So I'm going to be introducing the VLBI results that we have from the 6.7 gigahertz methanol masers that was taken during a high mass protostellar accretion burst. So my affiliations is EA Core, NAOJ, and CUSI. And today's talk is on behalf of the Maser Monitoring Organization. So there's a lot of us, and a lot of people's effort went into all of these results, and a lot of results that's not mentioned here. But I just want to give my gratitude to everyone who's participating and supporting the M tool. So I should give a little bit of background on high mass stars. These are stars that are above 8 solar masses, and they really affect all branches of astronomy. So let me see if I can get rid of this. Yeah. So yeah, nucleosynthesis, planet star formation, black holes. And because of nucleosynthesis, they also influence the possibilities of life in the universe. But despite this, their formation mechanism is pretty relatively unknown. So they're very rare, and they form in, I've lost my cursor again. They form in deeply embedded environments where it's, here we go. Sorry, everyone, I'm trying to get my cursor back. Okay, can you see, I hope you can see this cursor now. So they form in deeply embedded environments like this, and they're pretty hard to observe. They also defy the kind of usual continuous accretion theories of star formation because the luminosities they should have, if they're accreting continuously, are lower than what we actually see. So an idea came along, which is this episodic accretion. If you see this blue line, this is the accretion rate against time. And you can see that these stars are predicted to accrete a large fraction of their mass in these very short bursts. So the bursts are quite rare, happening every 1,000, 10,000 years. They're very short, they last a few years or less, but they're very important to high mass star formation theory because that's where at least half of the mass, final mass of the stars is accreted. And they happen in gravitationally unstable disks. So these are disks which will be clumpy and having spiral arms. So far, there's not been really enough observational evidence to test these theories. The first high mass protostellar accretion event was detected in 2016. And so far there's been 3, S255IR, NGC634, and G358, which is what I'm going to mostly be talking about today. So a little bit more on the simulations. Typically, if you imagine this kind of scenario, you're going to have material free falling onto the disk area. And because angular momentum is conserved, this accretion through the disk is going to be pretty slow, but accretion onto the disk is pretty fast. So mass is going to be accumulating on the disk, which is going to make it gravitationally unstable. So this gravitational instabilities produce clumps and spiral arms. And when one of these clumps or spiral arms accretes onto the star, this is what when we get a accretion burst. So over time, as the disk becomes more massive, it gets more unstable, it has stronger fragmentation. And so over time, you get these larger accretion bursts start to occur. So they start off pretty small and then they get larger. So the predictions of these simulations, there's quite a lot of them, but the ones I just kind of want to mention here is that the massive cores, so these kind of purpley ones, they tend to have shorter, more intense bursts. Shorter bursts tend to be more luminous, this is burst duration against luminosity here. You have this kind of bimodal behavior. And then the more massive disks tend to have larger bursts. Finally, the disks should exist and they should be clumpy, etc. So these are some predictions coming from the most recent simulations of high mass star formation theory. And our job really as observers is to provide tests for the simulations so that then the simulations can be refined. So what we really need to be doing as observers is finding bursts, investigating the progenitors, so the core mass, disk mass, age, and so on. Then intensely investigate the burst events themselves, so how much mass was accreted, what was the accretion rate, burst duration, etc. And then we start to correlate these parameters and compare with predictions from simulations. And then this allows us to then refine the next generation of simulations. So 6.7 gigahertz methanol masers are the kind of ideal tool for finding these events. This is because they exist in the disks of high mass stars close to the star, and their brightness is highly sensitive to changes in the radiation field. So you have an example here from S255 where there was this is one of the past accretion events, and you can see the continuum emission, which will be tracing the accretion, and the maser emission kind of follow each other very well. The thing is, the methanol masers are, I would say, a lot easier to observe because most radio telescopes will have a C-band receiver, and so you can monitor these, and they're very bright, because they're masers. And the other thing I kind of want to point out is if you look at the increase in flux, right, we get like 1,000 times increase in flux during an accretion event in the masers, but in the continuum, you typically get less than 10 times an increase in brightness. So really, in terms of accessibility, masers are just an excellent choice for trying to find these burst events. So with that in mind, with many things in mind, but with that as one of the things in mind, we set up the M2O. I'm not going to go into too much detail because there's a poster on this, which you can check out. But basically, we have a lot of radio telescopes that are monitoring a lot of masers. And when one of those masers flares, we then have these kind of observational resources for doing follow-up observations. So we have all of the main VLBI arrays, and then we also have things like the VLA, Subaru. We even got time on the James Webb, which will be launching hopefully in October this year. We also have some kind of development projects, for example, the single baseline interferometer, and there's a poster by Janis Steinbergs on that also in this conference. So the G358 event, basically, the Hitachi 32-meter telescope was monitoring this maser in its regular list, and it just started to see this 6.7 gigahertz methanol maser flaring. So we kind of distributed this information throughout the M2O, and we started doing a lot of follow-up observations. And for example, the ALMA TOO data we got identified which core was housing the methanol maser. And so then we could really zoom in on this as the progenitor. So then we did Zsofia Grand and got some archival data to look at the SEDs. And we found that, it's definitely a high mass star, and we could work out how much mass was accreted, the accretion rates, and so on. Then from the maser monitoring, just with radio telescopes, we can work out what is the kind of duration of the burst. So with this kind of system, have an alert network finding these events and then following them up, we can really characterize both the progenitor and the burst parameters, which then allows us to do comparisons with the simulations. I'm going to be talking about the VLBI parts of the results. How am I doing for time? Okay, 8 minutes. I'm not going to bore you with details on the data reduction, but I can assure you it was very fun. And the results basically look like this. So these are results from the LBA, EVN, and a VLBA. And what you can generally see, so this white cross is the position of MM1, which is this one here. And the mesas typically form these like generally circular distributions around MM1. And over time, so you can see the times of these observations on the burst timeline, you can see that the distribution of methanol mesas tends to get further from the star. The way that we interpreted this was not that the gas is moving. The gas is, the disk is full of methanol gas, but as the heat from accretion moves outwards, it creates the right conditions for mesas. So initially, the region close to the star it's around about 150 Kelvin or so. That's where the methanol mesas are being produced. And as the heat wave moves outwards, then you start producing mesas further away. And the mesas in the center disappear because it's maybe too hot or the conditions are just no longer right. So we saw this heat wave of energy moving out through the disk, traced by the methanol mesas. So if you kind of measure the propagation of this heat wave, so these are the different VLBI epochs overlaid on top of each other in different colors. And those colors also are matched with these colors on this radius against time plot. The data points corresponding to the radius of the mesa distribution are here, and you can see it starts with a very initial rise. So the heat wave is moving very quickly, and then the heat wave slows down to this continuous kind of linear trend in time. So around about 660 AU, you have this turnover point between the fast expansion at about 7% the speed of light to a slightly slower expansion of about 1.3% the speed of light. And this could be because, for example, that's where the methanol snowline is. And beyond that radius, you need to break the methanol off of the dust grains into the gas phase to produce mesas. And that's going to take energy out of the heat wave. Finally, the ring trick, at some point, the mesa ring shape disappeared. Maybe the heat wave reached the edge of the disk, or maybe the internal heat source switched off. These are all things that we're still trying to interpret. And we have a kind of team of people who are doing the radiative transfer modeling, and we're trying to figure out between us, based on the radiative transfer and the observations, what's going on. The kind of cool thing that we realized we could do with this then was that if you take each of these spots, so you remember I said that this is not a motion through the gas disk. The gas disk is stable, we're just illuminating different radii. If you add up all those different radii, let me see if this works here. You start to compile a kind of more full image of the disk as the heat wave moves through it. So I'm calling this heat wave mapping. It's just an easy name because we've already used the word heat wave now. And if you compile all of these mesa spot maps, you get this kind of combined disk spot map. And we can now start to see substructures and velocity trends in the disk. So if you take a PV cut across, like perpendicular to the highest velocity gradient in the disk, you get something that looks like this. And this is, tantalizingly looking kind of Keplerian. And the simulations require disk substructure and Keplerian disk. So we start to think that maybe we're onto something. So we did a bit more of a detailed analysis, and I'm gonna have to speed up just a little bit.
2 minutes.
Okay, thanks. We've initially just fit straight line to the velocity profile in log space, which gave us very, very well constrained confirmation that our profile is Keplerian. We then fixed the fitting to a Keplerian and fit for the enclosed mass. And the enclosed mass then was very well constrained. However, it's, what's the word? It's correlated with the inclination. So you can't really distinguish between the two. It's mass times inclination squared. So based on a kind of face-on inclination, you get something like 9 solar mass for a pretty face-on system. And this is matched with what we got from the SED analysis. So that's reassuring. Then if you take this combined spot map and you unwrap the polar axis. So this is the azimuth angle plotted against the radius. You start to see these structures. And now if you do this in log space, then any kind of spiral arms will look like straight lines in this unwrapped polar axis plot. And what we did, so there's a student, Yuri Uno, she's been helping me with the programming for this. We looked at what's the density of spots that line up in a particular direction. And we found that at a pitch angle, well, at an angle of 62 degrees, we get these peaks where there's a lot of masers that line up. So it's basically like trying to fit lines to this data, but it's not as easy as it looks. And we find that at a pitch angle of 62 degrees, we get these big spikes, which would correspond to logarithmic spiral arms if they're there. So these are something like 3 sigma detections, or just a bit over 3 sigma detections. Now, if we plot those, then we get this kind of plot, and we make some assumptions on symmetry. But basically, what we're seeing is very consistent with the idea of a global gravitational instability in the disk. Just to bring this to the conclusions, so we found this 2-phase heat wave. So the heat wave slows down as it reaches a particular radius. Then using this heat wave mapping, we've been able to confirm that this is a Keplerian disk with an enclosed mass of about 9 solar mass, and we find these spiral arms. We know also from the SEDs that this mass is about right, and that this is an accreting burst star. So basically everything that's kind of hoped for in these predictions, so a high mass YSO with a Keplerian disk, spiral arms and accretion bursts, this all seems to be coming out in this G358 event. So all of our results are currently very strongly supporting the simulations. And I don't really have time for future work, so I'll just leave this slide up and go to questions. Thank you very much.
Thank you, Ross. Thank you very, very much. Andreas, do we have questions?
Yeah, so we have one question from Paco. So M2O is a great initiative. Do you see any source where maser superbursts of different molecules or species occur, even with some time delay?
Yeah, so one of the interesting things about G358 was we threw a lot of single dish telescopes at it as quickly as possible. And there's a paper by Gordon MacLeod et al. Where they do these, let me just find an example. They do these kind of waterfall, what would you call it, light curves, using a bunch of different transitions. And you can start to see that there's delays in certain transitions. And this is something that's kind of an art in itself to interpret. But yeah, those things exist, and we're looking into it.
Okay, good. So there's another question by Hoyp. A Keplerian disk assumes gravity is the dominating force. How does this compare to other methanol masers?
Well, I think the methanol masers are just in the disk, and the disk is behaving, it's dominated by the central mass. So I think if you were to trace any thermal line or maser in this same disk, you'd get the same result, whether it's methanol masers or not. The only thing is that we could do this because this is very high spatial resolution. These are milliarc-second scale things. So this whole disk region I think it's about a couple of 100 milliarc-second size. It's very small. So the only reason why we found this and it's so well constrained is because we were fortunate enough to get so many VLBI observations that traced all the different radii as the heat wave moved through. So it was just a lucky event. But I think, yeah, if we'd have done the same thing for any other molecule in that disk, I think we'd get this pretty much same result.
And there is another question on Discord by Chris Phillips. Given the LBA, VLBA, and EVN have very different UV coverage, sensitivity, and so on, how well the various images from different epochs match? And I think I would like to add, how do you do the astrometric alignment?
Yeah, so in terms of astrometry, we used a phase reference source, and it was the same phase reference source used by the ALMA observations and everyone else. And that gave us the position of GMM1 here. Then regarding the different arrays, I recognized pretty quickly that because what you can see in this plot, the beam size is always different. And because of that, any discussion on the flux density is pretty much useless in terms of comparisons. Even between the two LBA epochs, the array configuration was different. Same for the VLBA. So I threw away any discussion of flux. And all of this discussion is just based on line of sight velocity and position. So that's why we concentrated on the PV diagrams and this kind of stuff. None of this is weighted by flux, yeah, because that would be a mistake.
Okay, and then there's more probably a joke question. Have you considered magnetic fields? But maybe, well, do you have any polarization information?
Yeah, so all of these observations were, we included polarization calibrators. I haven't done the data analysis for it just because it's hard. And currently there are not many people who can interpret the results, even if you do the data reduction. So I haven't, it's possible to do it. I haven't done it. One thing that is interesting though is Shari Breen's observations with ATCA had much better parameterization of the magnetic fields. And if we just compare the spectra from the VLBI and the ATCA observations, work out which spectral feature is which spectral feature in the VLBI maps, you could potentially then make some approximates on the magnetic fields. But yeah, as most people in all of history, I don't have a good answer for that question. I'm sorry.
Okay, thank you very much. I think we have to move to another speaker. Thank you, Rod. Thank you for answering a lot of questions. So please move to Andrey Sobolev. Talk. VLBI studies of accretion onto young massive stars. Synergy with single dish monitoring at sub-millimeter infrared observation. Andrey, please share your screen. And let me remind you that you can also raise your hand and you will be unmuted if you prefer to ask your question here on the audience. Andrey?
It seems we've lost Andrey. I'll try and see if he's in the participants.
So, okay, so maybe if Juan is ready, then we could switch our speaker.
Sure.
Yes, Juan Climent, he will be presenting uncovering the radio emission of low mass systems. So please share your screen. Sorry for the stress, but you are ready.
Sorry, now.
Okay. Andrey, yes, Juan will start. So we have time.
The problem was that someone switched off my status. So I couldn't.
Sorry, that was me. Sorry, Andrey.
Andrey, so just you will be after Juan, okay? Is that okay? So no problem.
Can you see
yes,
the screen?
I can see the presentation.
Okay, thank you.
So,
thank you, Anna.
please.
Yeah, so good morning, everyone. My name is Juan Climent from the University of Valencia in Spain. And today we'll be uncovering the radio emission of low mass stellar and substellar systems. So this is the first ever brown dwarf discovered through its radio emission. The previous detections of these objects always were firstly detected at infrared wavelengths and then at radio wavelengths. It was a great discovery published last year that made use of the low frequency array, LOFAR, observing at 144 megahertz. Now, this is important as most of the exoplanets and ultra-cool dwarfs are expected to emit at such frequencies or even lower. However, the majority of detections right now come at gigahertz frequencies, not megahertz. This is because our current instruments are much more sensitive at these higher frequencies, but also because some of these ultra-cool objects present extreme magnetic field strengths that will consequently emit at much higher frequencies than expected. Now, I need to make you an expert on the radio emission in ultra-cool dwarfs, so let's start with some observed properties. First, and just to be clear, we define an ultra-cool dwarf as any object, stellar or substellar, with spectral type later than M7. And surprisingly, they were detected at gigahertz frequencies as early as 2001. And from the surveys, we know that about 10% of them emit at such frequencies. And this emission can be actually separated in a quiescent or more stable part, which is always present, plus a rotationally modulated burst emission that is present only in some of them, like the one we have here on the right. We typically explain the radio emission in these objects by the gyrosynchrotron mechanism and auroral emission. And also it's worth noting that studying these objects is critical to better understand how these mechanisms play out here, but also how they may play out on exoplanets. I already said that most of the exoplanetary radio emission is expected at lower frequencies, but as we shall see in a moment, gigahertz observations may also give us some very valuable information. These are the known radio-emitting ultra-cool dwarfs in circles here, the detections. The non-detections are plotted in triangles, and this plot is from pre-COVID times, 2019. Since then, a few more have been added. And as one would expect, the majority of observations are here in the earlier types, and the majority of detections as well. But recently, more and more very cool objects have been observed and detected successfully in some cases. From this work and recent investigations of Cao and collaborators that are just about to be published, we see that L dwarfs may have a suppressed radio occurrence rate compared to M and T dwarfs. The binary systems are much more likely to meet than their single object counterparts, and that youth does not seem to actually enhance the quiescent radio occurrence rate of this kind of objects. Now, in addition to these three properties, we also know that the rotation speed of these objects plays a crucial and important role, as a fast rotation period helps to maintain powerful magnetic fields, which in turn are responsible for the detected emission at gigahertz frequencies. Now, in this plot that it's adapted from Tanya and collaborators, you can see that some of the ultra-cool dwarfs with known rotation periods, okay, they are plotted in crosses. The non-detections are shown in black squares here, and while the detections are in small red triangles. The three big triangles, these ones, are, well, these are detections with VLBI arrays. So that's very compact radio emission. And as you can see, all of the objects detected have rotation periods lower than about 4 hours. Finally, as I promised, let me touch briefly on the possibilities of exoplanetary radio emission at these frequencies, while direct detection is expected at much lower frequencies, as I said before. There have been some efforts in describing the possible interaction between an exoplanet and its host, star or brown dwarf. For example, this work by Penny and collaborators, published in 2018. In this plot, this is for the TRAPPIST-1 system, and they predicted fluxes not detectable right now, which are the solid lines. These are quiescent fluxes, but bursting emission that we indeed could detect with arrays such as the VLA, which would be these dashed lines. Following this work, actually, we proposed some radio observations of interesting systems such as TRAPPIST-1, among others, and we will be working on them and publishing hopefully very soon. But for now, what I can tell to you is that Pérez Torres and collaborators already studied this possible interaction in Proxima Centauri, and they found a very promising result of radio emission consistent with the orbital period of the planet. So this is a field that may open a new and actually a fascinating window for studying exoplanets. And finally, to finish this introduction, let's talk about VLBI studies of ultra-cool dwarfs. While dozens of them have been observed, only 3 detections have been published successfully. The first one, this binary, the authors, from the detailed observations that they had, they got a lot of information. Just to point out a few, they were able to obtain the dynamical masses, which is very important for theoretical models, as I will show you in a few minutes. But also they resolved the radiation emission, as you can see in this picture, and saw that it actually originated in only one of the components, despite being very similar, both of them, very similar in mass, I mean. Now, the next ultra-cool dwarf detected was published last year, and in this case, the authors detected emission in both components of the binary, and they also determined very precisely, as you can see here, the dynamical masses. In addition, well, they place a strong upper limit on exoplanets that may orbit this system. Regarding this very last point, last year as well, it was published the very first astrometric detection of a planet at radio wavelengths. This is the third ultra-cool dwarf detected with VLBI. And as you can see in this plot, after well, first obtaining the parallax and proper motion, and then subtract them, correct them, they found a hint of a companion here in the residuals. This companion will have like these characteristics that I just say here. So now, sorry for the very quick introduction, but now that you are an expert and you have well, at least a very good understanding of what an ultra-cool dwarf is and how we think that it emits at gigahertz frequencies, let us study an intriguing system together. VHS, as I'm going to call it, is a very young triple system with these masses that you can see on the screen, an almost equal binary and an L7 companion. And the system is located 22 parsecs away, so it's quite close by. Now, from previous work, we already knew that the central binary presented radio emission at 8.4 gigahertz, but not at 1.4 gigahertz. This is VLA data. And this detection was compatible with gyrosynchrotron emission, as you would expect based on what you already know. We predicted the turnover frequency to be somewhere between here, between 5 and 8 gigahertz, which implies a magnetic field strength of the order of kilogauss. But we wanted to make sure that the turnover frequency was indeed there. And if so, with these expected fluxes, we should be able to detect it even with VLBI arrays. So what we did was we observed with eMeRLI, the EVN, the VLA at 33 gigahertz, and also analyzed archival data, at 6 gigahertz. We also observed with NOEMA and ALMA, covering a very wide range of frequencies. We found no detections with VLBR, no with higher frequency observations, NOEMA and ALMA, but but these results were very interesting when you put them together actually with the detections that we did have, and I show them to you here. They are clear and resolved detections of 6 and 33 gigahertz at the expected position of the central binary. We found no bursting or polarized emission, indicating a quiescent emission. And from this alone, we cannot know whether the emission comes from one or both of the components. But when you put together all the constraints from the detections and non-detections, we found the following. The emission at 33 gigahertz appears stable over 9 days. The one at 6 gigahertz probably during 3 years. The lack of detection with VLBI arrays tell us that the emission originates either in both components of the central binary with a reasonable flux ratio, or in a region with a huge size that you have here. Also, we found no variability during the observations at 6 and 33 gigahertz, which means that the flux must be emitted in a homogeneity, in a region with a high degree of homogeneity, or in radiation belts around each component of the binary, similar to Jupiter's radiation belts. I would like to emphasize that the EVN played a crucial role here in determining whether the emission came from one or both of the components. I also told you that non-detections are also important, because in the case of ALMA and NOEMA, they ruled out the possible presence of a debris disk similar to this one with these parameters. That would be this line here, this blue line. And finally, after testing a lot of different models to explain these observational points, we found that the model that best suited all the constraints from detections and non-detections is not actually the one that I'm showing you here, is this one. And the scenario is represented by the dashed and dotted lines, which are simply different magnetic field strengths. And this scenario corresponds to a scenario where both components of the binary produce radio emission at radiation belts through the zero-synchrotron mechanism. We also place some limits on the plasma characteristics, although they should not be taken as definitive, since, well, these numbers came from simulations that we use more as a proof of feasibility, more than anything. In the future, we will certainly need multi-frequency, almost simultaneous observations to rule out variability completely, and also to see what happens at higher frequencies, 40 to 50 gigahertz. Now, moving on, beyond what we already talked about in the introduction, I wanted to present to you a very convincing reason to have some work done on astrometry. And well, let me say it, stellar evolutionary models are awesome. They are often used to predict masses of young stars from observational estimates of their luminosities and effective temperatures. And from these masses, one can better understand not only the individual stellar evolution, but also entire star-forming regions through the initial mass function. And they work great. I mean, look at this plot comparing observed and theoretical mass radius relationships. It's almost too good to be true. Well, this is because it's not the entire picture. This is the complete picture, and as you can see, it's not as pretty as before. There's some issues here with the low mass objects, but perhaps it's just this model. Well, actually, no. When you use different, different models, you see that well, basically the same behavior happens here. Just as I'm short in time, let me tell you that the discrepancies must arise. We know that they must arise from two factors: inaccurate observations or some key underlying physics that we are missing. In any case, what the author says is basically the same in all cases. We need more dynamically determined masses. So to do that, you have three options right now, but we are going to focus today on the astrometry, on astrometry in binary systems. And for this, I wanted to present to you these 5 low mass binary systems. Here they are, whose age is known. They have hints of possible radio emission, although none has been detected yet. And the binary separation is such that further VLBI observations can determine their dynamical masses. So some preliminary results. Out of the 5 binaries, we detected emission with three of them that are now ready to be observed with VLBI arrays, such as the EVN. So, but this is not all. I saved the best for last. I hope I have just enough time. We also observed 4 ultra-cool dwarfs with the EVN that had known radio emission. And I'm very happy to present to you the first results that we have just finished, and we will be publishing together with new already observed EVN data. We found compact radio emission in all of the 4 objects studied, and remarkably, the detected emission coming from one of the components of this binary. After this detection, we looked for archival data and found the detection at 8.4 gigahertz here, which means that together with this archival data and the new data that will arrive soon, we should be able to obtain the dynamical masses and hopefully much more information only available through this kind of observations. And just finally, we saw compact emission from the T6 dwarf, the coolest so far ever detected with this compact emission, which is 100% circularly polarized, so probably bursting emission, of course, that we will have to analyze more deeply together with recent EVN observation. This detection, let me say it, is remarkable because it can also contribute to discover and characterize orbiting planet around this object, either through induced radio emission or through the reflex motion. And finally, we can also probe the morphology and evolution of the auroral radio emission in this object. Sorry for the speed, but thank you very much for your attention.
Thank you very much, Juan. Andreas. Please check the question.
So there are no questions yet, but maybe I can start with one. So for the source which you detect with the VLA, but not with VLBI, what's the flux difference between your detection and the noise limit you have with the VLBI?
You mean, sorry, I cannot go back. Can you see the screen? Can you?
Yeah.
Okay. I cannot go there. I'm sorry, there seems to be some problem. But you mean the detection with the VLA and not VLBI, right?
Yeah, exactly.
Yeah, so there were the ones, it was just one of them is just above 5 sigma. And the other ones, we have almost, I think if I can recall, almost 7 sigma detections. Yeah. Yeah.
No, but
sorry, perhaps.
How does the flux in the VLA image compare to the noise in the VLBI image?
Oh, you mean, so the flux in the VLA image, I can't show it to you, but okay, right now. The flux here, for example, are 178 microamps per beam. This is one of the highest one, I think. And the VLBI, in the case of the EVN, for example, we are getting somewhere between 15 microamps per beam.
Okay.
Something like that, yeah. Thanks.
Okay, I don't see any question in the Q&A, in the chat, or on Discord.
Anyway, I'll be available through Discord, of course.
Okay, thank you. Thank you very much.
Thanks.
So let's allow to share the screen to Andrey Sobolev. We are coming back to major topic, VLBI studies of accretion onto young massive stars, synergy with single dish monitoring at sub-millimeter infrared observation. Please, Andrey, go ahead.
Okay, so our talks are very complementary with Ross' talk, but repetition is the mother of education, of learning, so that's okay. We will see on the look at the things from the different angles. My topic is about the synergy. How much do they help each other, and what can we do? First of all, interferometry is crucial for the studies of accretion events and accretion structures. This is one of the good images obtained with ALMA, where we see the gravitational and stable accretion disk, and we see different structures here on different sizes. There are streamers in the right panel. There is a kind of ring in the central panel, and so on. But all of these structures are either big or faint to be observed with VLBI. So what can VLBI help in the studies of these accretion structures? First of all, there are masers in these disks, not always, but quite often. As a result, we can observe these masers, and masers contain a lot of information. They can tell us about the radial velocities, they can tell us about the proper motions, unlike what we can have in the thermal structures of bigger size. Here, the same object by the same team, and here you see in the left panel the H2O masers which are tracing outflow, and in the right panel there are methanol masers which are tracing disk. So different observations and different masers, they complement each other, and that's very important. But if we can say that, for example, that water masers appear in the outflow, or methanol masers only in the disk, that's not exactly correct. For example, this image shows, here you see the shaded areas. The shaded area in the lower right corner, it is a disk, shows the disk, and in the left part, the shaded area shows you the outflow. And we see that here the masers, or methanol masers, class 2 methanol masers, they appear both in the edge of the outflow and in the disk. That's just because they have radiative pumping, and they are formed close to the to the source of radiation, to the young stellar object. But normally, if we look at where they are distributed, so these even in the inner parts of the outflow, they trace kind of Keplerian motions and so on. So this image shows you the view of accretion disk. And since we have both here, both radial velocities and propel motions, we see that there are Keplerian rotation. One of the things which is very interesting in this case, we see that the masers form structures. They form clusters, and these clusters form structures which are moving. And the rotation is not actually strictly Keplerian. There are some inward motions in this case, which is very important for the studies of accretion events. So in general, different masers, as I told you, form in the different parts. So we normally see the class 2 methanol masers in the disk or close to the young stellar object, that at some distance from it, we can see hydroxyl masers. Hydroxyl masers also very close to the disk, but in its other part, the difference is not so easy to interpret, but they are formed in slightly different regions. Maybe these are chemical things. So class 1 methanol masers, which emit at different frequencies, they are found in the outflows, and water masers also in the outflows. So these are the things which are have relation to accretion, and which we can study. The accretion disks around the high mass objects are actually, as Ross said, gravitational and stable, and they are not normal as we see and or axisymmetric. They have quite different structures. And the other thing is that yes, there are accretion bursts. So because the structure of the disk is very clumpy, so the material doesn't fall on the star continuously, and there are accretion bursts. So, and these accretion bursts are transient events. And to study the transient events, we need some special techniques. These transient events, they carry information on the sudden changes in the objects. Their characteristic times are short, and sometimes we can observe the whole duration of the event. That's very important because transient events are kind of phase transitions, and they carry information both prior and post-evolutionary phases. And this makes these events very informative. And monitoring is the only way to register and study transient events. But monitoring requires considerable time, and it is very hard to do, for example, in the millimeter and especially sub-millimeter infrared facilities. And further, it's almost impossible with VLBI. So anyhow, at present, extensive monitoring is ongoing in the maser radio transitions and brings good fruits. So there are different types of monitoring. There's spectral monitoring, photometric monitoring. And for example, one of them is All Sky. These are surveys like WISE, Gaia, and so on, in which we can find these transient events in their archives. Sometimes some selected areas are monitored. These maps, for example, this is JCMT transient survey and so on. But most often in our research, these are used the monitoring and selected targets, where we have list of individual sources which are monitored with some cadence. This is done in the Barak University, Hartrau, Torun, Pushina, and some other things. And the fourth type of monitoring is triggered monitoring. That means that we see that some event is happening and we have some expectations of its duration. And so we start this triggered monitoring, which this is very well done with VLBI. In this case, we also can use ALMA, SMA, and other interferometer and quite expensive facilities. So first of all, we need to select proper targets, and one of these targets is very good, is this S255. Here we see the disk, we see the outflow, and we see in the infrared also the indication that there is a disk here, which is perpendicularly to the outflow. So, indeed, in this source, there was detected in 2015-16 the accretion burst. In the left, the prior to the burst, and after this burst, we see these images. And in this case, the infrared were first detected the accretion burst, and they confirmed it. And after that, the studies of this object were done, for example, in VLBI. And in this case, we've seen only very, very interesting event. So the masers, they changed their position from one location to another location. And the locations of the maser spots are don't coincide. This was not expected, but this was something which tell us some new results, some new information about this. And then in the right panel, we see the monitoring. In this case, the time goes from low to the upper, it goes up. And we see that the source was relatively stable, then accretion burst happened. And what we see now is that the masers changed their location, at least their velocity. And we see in this case that these changes are, the masers don't go back to their position. So maybe they have the same general region, general location, but not exactly the same. This is very important because this tells us that accretion burst changes greatly the physical and chemical parameters of the source. So the other thing is that for the people of Burns and co-authors about water masers, and these water masers have shown that that there is an outflow here, and this outflow has some dynamic age, which tells that it doesn't appear from this accretion burst, but another accretion burst was existing before. So these are recurrent events. So they happen with some not periodicity, but with some time from one another. So there are multiple bursts. So these are other observations which show you how the jet is forming this right panel, and the detection of the new velocity fields which are detected in the other line. New maser line was detected in this source. Okay, another very interesting source in this case was NGT 6334I. So in this case, we see contemporaneous flaring in many masers, hydroxyl, methanol, and water masers. And in this case, the ALMA observations have shown that one of the sources in this location increased its brightness very considerably by a factor of 4, while the masers increased their brightness much more. But what we see in this case, that is okay. This is increase of brightness in the sub-millimeter region, while in the previous source we have seen increase of brightness in the near infrared, and this is very greatly different.
2 minutes.
Okay, so and then we have we see here this kind of flare, and we see the changes in masers. That's it. And we see the positions and so on. So the maser monitoring organization, it just occurred, and one of its advantages is that they managed to catch this flare and trace this flare and detect this translocation of masers. Okay, but what is very interesting in this case, so the further it was detected, these spiral arms, they were detected with VLA. And Ross already told about that we have seen that in this case, one of the sources increased its brightness. But what is very interesting is that this burst, in this case, was not detected in the near-infrared and could not be detected considerably in the sub-millimeter range. So it is flaring only in the fine infrared range. That tells us that we cannot use only one range to make conclusion of what's going on. So we have to use all of this. So one of the interesting things about these transient events that all of these accreted masses are masses of Jupiter. So these are not stellar masses, while the current models predict accretion events on the greater scale. This is something which asks us to improve our models. So currently obtained results on the maser triggered studies. So maser studies combined with observations in the fine infrared and so on. You can see that we see structures of the 1000 EU in size, that this accretion of matter goes along these structures. The accretion structures are inhomogeneous, and so this produces flares. And a large amount of high density matter is present in the disk structures, leading to a significant slowdown of the propagation of the energy released in the accretion burst, which was shown in the Ross talk by Ross. And what is very important, that after accretion burst, the physical chemical state of the disk matter changes and doesn't return to its previous state. This is something very new, which no one knew before. Some more you can see, this is a reference to my other talk about millimeter sub-millimeter transient events in star formation. You can follow this reference and find something new probably for you, and also for this synergy. So thank you for your attention. I'm ready to ask any questions.
Thank you, Andrey. Andreas, could we have questions? Do we have questions?
Not yet. No. Nothing in the chat and in the Q&A, and also Discord, nothing yet. So I just checked. So there are also no raised hands.
Everything was clearly explained. How often do the masers burst, Andrey? Once a year?
No, not once a year. But Ross told that it is thousands of years. But in fact, if you look at the S255, you will see that there are hundreds of years, 130, 170. So one or a few hundreds of years. So, but you should remember that all of these bursts which were detected at present, they were bursts which occur to accretion of the planetary masses. So these events should happen more often than the events of accretion of stellar masses. But at present, this is only theoretical prediction, but we have to work more on the theory in this case.
Yeah, so Kazi asked a very related question. So how come there are so few maser bursts? Does this tell us something about the length of the accretion phase in these systems?
Well, the length of the total accretion phase, yeah. Once again, so we don't have any detection of accretion of the stellar masses. At present, we have followed only 3 accretion bursts. So we don't have answer to your question. And we see that the theoretical models at present, they are reproducing the things only qualitatively, but not quantitatively. So if you say that, if you ask a question, how long is the accretion phase? That's something which we don't know. because we don't have enough observations. The time of our observations is all these accretion events were detected in 2016, while they lost, the accretion phase lasts for many hundreds or thousands of years.
Okay, so I don't see any more questions.
Okay, so thank you, Andrey, again. Let's move to our last speaker for the talk, Tanya Koryukova. She will tell us about the study of the Milky Way scattering properties based on multi-frequency VLBA observation for the AGN core sizes. After this talk, we will have a short poster talks. So Tanya, please go ahead. I can see your presentation. I cannot hear you. Tanya.
Sorry, now?
Yes, I can hear you. I can see you, and please show your presentation.
Sorry.
Okay, good luck.
It is okay, yes?
Yes.
Hello, my name is Tanya. 2 months ago, I defended my master's dissertation with this work, and today I want to tell you about the main results of my work. This work is devoted to the study of scattering properties of the interstellar medium of our galaxy. The interstellar medium is a rarefied medium that fills the space between stars in our galaxy. All of the components of the ESM are closely related to each other because in the galaxy there is a constant circulation between matter and energy. It is known that due to the interaction between stars and interstellar medium, turbulent motions and inhomogeneity are generated in the interstellar gas. So when a radio wave passes through a turbulent gas, it will encounter stochastic free electron density fluctuations on its way, which cause fluctuations in the refractive index. So wavefronts will be randomly distorted, and thus scattering of radio emission occurs. There are two main models of scattering screens that describe the observed phenomena of radio emission propagation through an inhomogeneous medium. First, it is Gaussian screen model. The brightness distribution of a point source seen through a Gaussian screen is Gaussian with a diameter is proportional to the frequency to the power of -2. The second model, this model is according to this model, according to which the spectrum of electron density fluctuations of plasma is modeled by a power law, which is consistent with Kolmogorov turbulence. The scattering angle in this case is proportional to the frequency to the power of -2.2. So if there is no scattering screen, then the observed angular size will be coincide with the intrinsic size, and in the case of active galactic nuclei radio core, it will be proportional to the frequency to the power of -2. To study the scattering properties of interstellar medium, we used active galactic nuclei because they are extragalactic sources. Therefore, the radiation passes through the scattering screens throughout their entire depth, not only through the part of it. For example, for pulsars, These sources are evenly distributed throughout the sky. And also we have a lot of observational data. And we use archival VLBI data of more than 9,000 active galactic nuclei in a wide frequency range from 1 to 86 gigahertz to measure the observed angular size, that is the diameter of apparent jet base, so-called VLBI core. Based on these measurements, we plan to perform a large-scale study of scattering properties of our galaxy. This work is a continuation of earlier 2015 work of my colleagues, but now we use a larger sample of data, new methods for modeling of the apparent jet base structure of AGN, as well as completely new approaches to study the scattering effects in our galaxy. Let's look at the results. We measured angular diameters for almost 4,000 AGN cores at 2 gigahertz, and it's a tropic distribution of the investigated sources over the sky allowed us to map out the distribution map, the distribution of sources sizes to visualize the angular broadening effect. Each pixel of this map contains average observed core size of active galactic nuclei that fall into a circular area of a 10 degrees radius around the central point. So red color of this map means the largest observed sizes, and the blue is the smallest observed sizes. The increase of the average value of measured sizes in the galactic plane is observed. The distribution, as we can see, the distribution of sizes in the galactic plane is not uniform, which indicates an inhomogeneous distribution of scattering screens in the galaxy. We have not found such regions with a strong scattering effect outside the galactic plane. So scattering effects is sensitive to electron density and its fluctuations. So therefore, we can expect an enhancement of the scattering properties in regions with high concentrations of free electrons. We have found the strong correlation between the distribution of AGN core sizes, these contours measured at 2 gigahertz, and H-alpha radiation intensity distribution in the galaxy. H-alpha emission that observed in spiral galaxies is a direct indicator of the ionized interstellar medium. And as we can see, contours of AGN sizes mostly repeat locations of high intensity H-alpha clouds. So we can conclude that there is a direct relationship between regions of high H-alpha intensity and the distribution of scattering screens in the galaxy. Due to the scattering, measured angular diameter of AGN core will correspond to a convolution of intrinsic and scattered component of observed size, measured size. If we consider a simple approximation to this, it will look like this. It is expected that K index is approximately equal to 2 if scattering dominates, and equal to 1 if when radiation coming from this source is not scattered. To estimate a K-index, we can use the data of simultaneous multi-epoch measurements of AGN core sizes at 2 different frequencies for each source. For example, at 2 and 8 gigahertz. Using the obtained values of K-indices calculated for 3,500 uniformly distributed over the sky sources, we created the distribution map of scattering properties in the galaxy. According to this map, we can highlight the region of strongest scattering effect in the galactic plane. It is the region of galactic center, galactic bar, and Sagittarius A star location. We obtained typical K-index values for unscattered sources. It is equal to 1, which is in a good agreement with theoretical predictions for AGN cores with synchrotron self-absorption. As we can see from the map, these sources will fill almost the entire sphere except the galactic plane. Typical value for scattered sources, it is here, is much less than 2, since we are considering only an approximate equation for the frequency dependence of the size of source, which doesn't take into account the contribution of 2 effects. On the right side of the slide are the results of earlier work of my colleagues. The results are slightly different from what we got now, but now we got a more accurate result. And now let's look at the results when we take into account the contribution of the intrinsic and scattered components of the observed size. This figure shows how the AGN core sizes changes depending on frequency of observations for 2 different sources: unscattered source, it is blue one, and a highly scattered source, this red dots. As you can see, the observed data for these 2 types of sources fit differently. And using the multi-frequency observational data of AGN core sizes in galactic plane, we can estimate the value of scattering index, which will correspond to the best fit of the intrinsic and scattered sizes at 1 gigahertz. Thus, we performed feeding for 4 subgroups of sources, obtained values of scattering indices summarized on the slide here. And also we used an alternative method to estimate the scattering indices. We compared the size distribution of scattered sizes and unscattered sizes, and the distribution of scattered sources was fitted with a function. Those parameters were used to calculate the scattering index. The value we got is indicated here. Okay. And let's summarize the results. We obtained the most detailed to-date map of scattering properties in the galaxy based on observations of AGN core sizes. We determined that scattering screens are mainly concentrated in the galactic plane, but the distribution of these sources is highly inhomogeneous, we estimated k-index for unscattered sources. The result is in a good agreement with the theoretical predictions for AGN core with synchrotron self-absorption. And we calculated the power law scattering index using multi-frequency observational data, but now we cannot conclude which model Gaussian or Kolmogorov or scattering screen model describes the observed data better. The selection of better model maybe will be done in our future work. And of course, it is possible that both models are appropriate, but in different parts of our galaxy. And also, more observations are required to test each of the models locally. So this is all the results. Thank you for your attention.
Thank you, Tanya. Thank you very much. Let's go for questions.
So Hope has a raised hand, so maybe he can get.
Yes, thank you. I'm here. I didn't have a camera, but that doesn't work apparently. Congratulations, very nice talk. I have many questions. Can you go back to the distribution of the K1 on the sky? Yeah, that one. So no, the other one. Yes, this one. So that's quite an interesting result. And at first I thought that looks like you detected the molecular ring in the inner galaxy. But then I realized that maybe the galactic center region is underrepresented because of optical depth effect. So I would assume that the galactic center has the highest K index, but maybe you don't detect as many sources there because of free absorption.
I'm really sorry. This was the question.
Yeah. So the question is it possible that the galactic center is underrepresented in your plot because of galactic absorption? So you don't have as many background sources?
Yes. So as we can see in this region, we have like two clouds. And this is the result of this, that in this place we can observe a little bit less number of sources when, for example, here.
Yeah, okay, I understand. Very good. It's very interesting. I don't know if there's more time. Can we also look at the H alpha distribution?
This.
So it's very clear that in the galactic plane, there is a clear correlation. But I think it is curious that there are some higher latitude regions of enhanced scattering which don't have H alpha counterparts.
These regions of...
Yes, and also in the south, yes.
Yes, but here is
Southern hemisphere avoidance, yes.
I don't really know what's exactly these regions are, why we observe here and extended sources. But this is a very interesting result for our future work. Maybe here is some of here and maybe in some other places, some of local screens, scattering screens, not H alpha.
Right, yeah, I think it's very interesting. I agree. Thank you.
Okay,
Very nice work.
Okay, so we have more questions. One is from Sander Frey. Excellent work. Did you also try to plot the locations of known intraday variable AGN radio sources to see if there's any indication of a connection with your map of angular scatter broadening?
To map out the variability of.
No, so there are these intraday variable sources that also show strong scattering. And did you check whether that corresponds to like the locations to what you see?
No, we didn't tried it now, but maybe in the future work. We just use all the data we have to study this some kind of large scale properties. To see if there is the model is dominated model of scattering screen, so on. And
okay, and finally, one question by Yun Yang. Nice talk. How many sources do you have in the galactic plane?
In the galactic plane, I can say for this map. This is the simultaneous measurements of AGNs at 2 and 8 gigahertz, and in the galactic plane we calculated the K index for almost 500 sources, and outside the galactic plane it was around 2,000 sources. It's like these numbers.
Okay, and would it help to get like a denser sampling in the galactic plane?
Oh, I'm sorry, can you repeat? I have.
So would it help if you had more sources that you can do in the galactic plane?
Oh, of course. If we have more sources in this region, as you can see, where we have this hole without data, it will be interesting to see what will happen here. But,
okay.
And of course, it's more detailed map. Maybe we can construct.
Okay, thank you very much. So let's move to the poster session. Tanya, could you stop sharing the screen? Thank you. Artis Aberfelds, he will tell us about the high mass star forming region IRAS 2126. So Artis, 2 minutes, please. Yes, we see your
Hello, everyone. Can you hear me?
And we can hear you. Yes. And we see you.
So let's go full screen. So this is my first presentation about my work with VLBA data. I'm mostly working with single dish data, and we make team from Latvian and Polish scientists, including our chair lady Anya. And I will speak about very famous massive young star IRAS. His name is here. And from single dish data, we saw that the source is quite variable. And in this monitoring campaign, we found that many spectral features actually disappeared and fall below detection rate. And as previously made VLBA observations was quite old, we hoped that we will see some structural changes and found possible explanations for vulnerability. But observations found that there is actually very small changes in source overall structure, comparing our data to 15 years old or with newer data. And this source was quite well studied by Gabriele and by Luca. They found the distance and parallax and studied magnetic fields. So we decided to look how individual cloudlets are changing during this time. And we found several interesting changes. In total, we found that several, in this case, 7 spots has survived all 15 years from oldest epoch to our newest epoch in 2019. So I will show only 2 cloudlet results because we have very limited time. Here in the left, you can see quite a large change in structure from this V shape to quite linear in later. Also, the position angle is changing from epoch to epoch, and this cloudlet number 5 is brightest cloudlet in all epochs because it's main contributor from all the flux what we can observe in single dish or in VLBA. And here we can see interesting new tail appearing for blue shooter part, extending this feature from approximately 13 astronomical units as it was found before to quite large 35 astronomical units found in our epoch. So dashed lines was maximal distance and solid one was simply train light feet. And that's all I think I managed to include in my time. Please see our poster and wait for publication a bit later.
Thank you, Artis. And let's discuss in Discord, for example, in the Discord channel Science Galactic. So let's move to Agnieszka Kobak. Agnieszka Kobak will also present some details about the high mass star forming region, another one. Agnieszka, are you here? Yes, we are seeing you, and we don't hear you. I don't hear you. Agnieszka.
Yes, now
yes, I can hear you.
Yes, hello. On my poster, I present the result of methanol muscle burst in high mass young stellar object. So first we have long-term observation from a single dish antenna. You can see result here as a dynamic spectrum. In the 2019 year, we have observation via 3 interferometers, and here is this result. This is 6 epoch, but this first is before the burst, and that 5 rest is during this burst. So we can compare the spectra and these distributions. For this whole structure, additionally, we have 2 more transition. This is 20.2 gigahertz methanol and 22 gigahertz water vapor muscle, and you can see coincident these 3 transition here and compare these spectra. And because of these both transition methanol muscle, which is there, they are overlapping. So we have present they coincidence here. And thanks. That's all.
Thank you very much. Zsofia Szabo will tell us about episodic ejection from a low mass young stellar object traced by the water maser. Zsofia?
Hi, so can you actually hear me?
I can hear you. I don't see
great.
yes, but okay.
Okay. I can share my screen for some reason. I will try again. So can you see
yes.
it now?
Yeah, we see.
As well?
Yes.
Okay, great.
Go.
So Hello, everybody. My name is Zsofia Szabo. I'm a student in Hungary, and this is our poster on IRAS 16-293-24-22. So the life cycles, as we know, stars are based on their initial mass. However, accretion bursts are common in both low mass and high mass star formation, and much progress in the study of high mass star formation has been made in recent years with the study of masers and also discovering new species of them. So about our source, this is a well-known and well-studied low mass binary system in which water maser emission shows a cyclic character and traces episodic ejection events. So in 2020 September, thanks to the Maser Monitoring Organization, a new and so far the strongest water maser emission was detected in this system. So in a collaboration, we submitted an EVN proposal in order to study this enhanced maser activity, and our observations were carried out this spring with the requested longest baseline. So fundamentally, our aim is to provide comparisons between low and high mass star formation by investigating the outflow behavior of a prototypical low mass system. So far, we were only able to recover about 10% of the total maser emission, even with this baseline. Therefore, the missing region from which the flare originates has to be very compact. So at the moment, we are working on preparing images of the maser emission in order to answer the main question, where does the new maser flare come from in the system? So we are planning to submit a VLBA proposal to study this object further. And if you are interested in our work, please feel free to find it in GatherTown. And I'm also happy to chat about it later tonight. Thank you very much for your attention.
Thank you, Zsofia. And the last poster by video, again, Ross Burns, about the activity of the M2O, Maser Monitoring Organization. Benito, you will share the video, right?
Yeah. I will start now. Poster is about the recent activities of the Maser Monitoring Organization. We call ourselves the M2O. And the M2O is essentially a small research community involving researchers across wavelengths and disciplines, generally pursuing maser-traced transient astronomy. So I only have one slide. There's more information on the poster itself, but I really wanted to focus on one aspect that served our community very well, which is the mode in which we operate. So everyone involved is basically contributing whatever time they have to spare. So we needed to make a kind of system that kind of gives more than it takes in terms of investment returns for the effort that you put in. So basically you have a bunch of radio telescopes that are monitoring masers, and they've been doing this for a long time. When they find a new transient event, so a maser flare, they'll then tell the M2O, and we have this communications network where we then disseminate this information to a bunch of other facilities and theorists and experts, with the permission, of course, of the monitoring station. We're then going to do a lot of follow-up observations of the flare to try and figure out what caused it. So when we've done this before, we find things like accretion bursts and whatnot. The important thing then is that we have this communications network where we can discuss the event in the context of the expertise of a lot of different disciplines. And then finally, we bring everything together to publish papers. And the important thing then is that all of the papers will credit the original team that discovered the maser flare. So that helps the maser monitoring telescopes, keep maintaining their funding and to keep giving us these reports. So it's really kind of a win-win for everyone. Check out the poster. Have a nice conference.
Thank you. Thank you all of you for the very nice, very good morning session, Galactic session. So we have a coffee break now. Denise, do we have any more announcements? So we will start at 11:20.
And thank you, Anna, and Andreas for great sharing. Good job.
Thank you. Okay, so see you 11:20. Thank you.
It's actually, it's really interesting having people be co-chairs because you really need to work together.
Yes, so, and yes, I like working with Andreas always, maser and not maser.
Yeah, I think that went quite smoothly. So that's a good way to operate.